Now, how we just move directly to the formula. We don't need to explain anything. We've already done these two formulas for effective duration, effective convexity. The formula is quite simple. It doesn't require so much into it. So we are saying interest rate risk, how we can be able to analyze interest rate risk, we say is minus effective duration times 100 times change in yield plus, you can put that in brackets like that, plus effective convexity times 100 times change in yield, but now squared there. Notice this change in yield is squared. Effective duration, you're saying it's minus because this is beginning with V minus V plus. This one is V plus V minus. So you can be able to see the similarity between the two right there. And now putting it all together, we can be able to see that this is the formula that is used to measure the degree of interest rate or the degree to which a bond is exposed to interest rate risk. Let's look at an example that can emphasize or reinforce our understanding. Durable company bonds have a duration of 5.6 years and a convexity of 38.2. The conversion force company bonds have a duration of 7.3 years and a convexity of 38.2. Determine which bond is exposed to more interest rate risk. We can be able to see that they both have the same convexity, both durable and conversion force companies. So we just apply the formula trying to measure interest rate risk. Right here, and we say example. I'm right here, and we've already been given the example, so now we're just going to solve the question. We just know that effective minus effective duration times 100 times change in yield, like that, plus effective convexity times 100 times change in yield squared is equals to EIRR, or interest rate risk, how we can be able to measure interest rate risk. In this case, the effective duration, we start with durable. So we are saying the effective duration is 5.6, so it's minus 5.6 multiplied by 100 times the change in yield. We are saying the change in yield given to us, in this case, determine which bond is exposed to more interest rate risk. The assumption will be that it is going to be a one-time parallel shift, a 1% change, so it's 0.01 right there. Then we add the effective convexity. We're saying the effective convexity given to us is 38.2. 38.2 times 100 times 0.01 squared. How much are we getting in form of the interest rate risk? Let's compute. So we have minus 5.6 times 100 times 0.01 there plus 38.2 times 100 times 0.01 squared. We have minus 5.21. We have minus 5.21%. Minus 5.21%. Now we also have the other company, which you are saying is conversion force. Conversion force. So we have the effective convexity as 7.3 minus 7.3 times 100 times change in yield 0.01, like that, plus we have the effective convexity is the same, 38.2 times 100 times 0.01 squared, like that. So how much do we get there? We have minus 7.3 times 100 times 0.01 plus, open the brackets, 38.2 times 100 times 0.01, close the bracket, 30.9, no, I'm getting, I think, pardon me, I think there is something, so it's minus 7.3 times 100 times 0.01, we have minus 7.3, then plus, open the brackets, 38.2 times 100 times 0.01 squared, we have minus 6.9 minus 6.9%. That. Now, from that, we can be able to try and identify the one which is exposed to greater interest rate risk. The one with the greater value right here is exposed to greater interest rate risk. So we say, therefore, conversion force is exposed to greater interest rate risk. Notice this is the same. You can see conversion forces got the same if convexity. They have the same convexity, and the only difference is that this one has got greater effective duration and then that one there. So that one has an impact on the overall outcome of the interest rate risk